Okay, then let's restart the seminar. Then I already skipped the 50 pages. The content is how get elucidate the chiral helix spin structure using the neutron diffraction and muon spin rotation measurement. But I skipped. Then let's start the special properties on the chiral magnet. One of the special properties is this one. This is the field dependence of AC magnetization. The one hertz is the blue one. This compound magnetically helical spin order at 38 or 37 Kelvin. They are ordered helix state, ordered state. But if we apply a high frequency AC magnetic field, they are going to the TC is going to down. If you consider the higher frequency going to lower TC, it is not the dynamics. Dynamics should be a higher frequency going to the higher temperature. But this one is if we apply the higher frequency, is going to decrease the temperature. What up? This is not observing the spin dynamics. This is the highest frequency, 1 kilohertz. We have something like anti-ferromagnetic ordering at 37 Kelvin, and like a ferromagnetic ordering at 35 Kelvin. Then we analyze carefully. This one is a magnetic AC response from this single crystal chiral magnet. This one is compared with racemic one. And this one is a higher above TC. The green is applied magnetic field, and the black line is applied magnetic field, and the green is a response from the sample. This is good, the sine curve at above TC. But below TC, just 0.2 Kelvin lower from this point, they are going to this response. What up? Same temperature, racemic is good, is normal. Yeah, this one is contains a higher frequency response from the AC magnetic field. The chiral sample can generate more higher frequency at third order or 5th order or 7th order, 9th order. We are applying this field. The response is more higher frequency. This is a very, very typical properties on the chiral, not only the magnet, but maybe the liquid crystalline is similar. This is a cartoon to how the makes Goldstone mode generate from the helical structure, chiral helical structure. And just this is extracting of the 3 omega, chi prime 3 omega response. At just below TC, we have big response. This is almost 10% of the fundamental response of 1 omega. But anyway, this is possible to understand by using the spin current of the system. This one is spin current generated by the motion of the Goldstone mode, number Goldstone mode of the helical spin structure. And finally, we get the S4, S powered 4. Yeah. Then we generate the third order magnetic response. But anyway, we can say the chiral system to generate a nonlinear response. And then finally, we can draw the phase diagram on this sample. The magnetic helical, chiral helical magnetic structure, all that at the 37 Kelvin. At the 35 or 34 Kelvin, they are ordered to the commensurate chiral magnetic structure. But this one is molecule-based, but also we can grow the inorganic metallic chiral magnet. These are some samples of the chromium, niobium, sulfur, and the iron germanate. This is the almost summary of the structure of the chromium, niobium, sulfur compound. The niobium S2 has a layered compound, and the chromium with spin, they are intercalate between two-dimensional layer, and the chromium makes a helix. And the chromium has spin 3/2, and then these spins align to helical order. If we grow the enantiomer pure crystal. And this crystal space group is P6322. And the pitch also we can find later by Lorentz stem, but we already know the pitch is at the ground state is 480 angstrom pitch. It's very, very long pitch compared with the crystal in itself. But this case is metallic chiral magnet, then we can use Lorentz stem. And this is a cartoon how to measure Lorentz stem. We are irradiating electron from the top, and we have a sample and magnetize. They have the magnetic domain, but this Lorentz force can bend to the electron transmission, emitting electron. Then we find some magnetic texture. This is sample. We cut it and makes a thin film on this chromium, niobium, sulfur thin crystal. And this is the result of the Lorentz stem at zero field. We are so surprised when we look this figure. You know, there are the pitch of helix is 480 angstrom, but this line of helix is perfect. There are no branch, no defect. And if we measure the electric diffraction measurement on this sample, here you can see the C direction is here. Then we can see 000 and 001 and 002 peak. The spacing is correspond to the crystal in itself. But if we zoom up this 000 diffraction, here is we can find satellite, only one set of satellite. This means the line of the helical pitch is perfect. There are no higher order diffraction, only one diffraction means. And this spacing corresponds to the 480 angstrom. If we zoom up, this 000 diffraction is getting this ellipsoid diffraction, and this size is correspond to the 3/2. This is coming from the chromium 3 spins. Then this magnetic structure is coming from the chromium spin, and the helical pitch is perfect, and this is correspond to these things. But of course, we can apply the magnetic field on the measurement. This is video applying the perpendicular magnetic field on this system. You can see the pitch of soliton is gradually changing from the 418 angstrom to infinite. length and go back by decreasing magnetic field. How stable this structure? We are curious of this one. Then we cut very rough thin part and the thick region part, and we measure the helix. No change the pitch. More roughly, but this is also no change the helical pitch. And diffraction is same. Then finally, the student makes a big crack on the sample. It's almost 1 micron hole. Then we check the helical pitch between the crack of the hole, but we cannot change the pitch by this one. This means the chiral helix is really stable. We cannot change any modulation on this system. This is similar. We can imagine how stable typhoon or hurricane or cyclone by the chirality. If we put the chirality on the storm, there becomes very stable and behave as a particle. And this one is also soliton is the sum of a particle. Yeah, this is the same. Yeah. But anyway, we can measure the number of solitons by using magnet resistance. This is single crystal, cut into single crystal, and C-axis, helical axis this way. We can measure the resistivity with this 4 terminal probe. And this one is the total measurement of the increasing field, a red line, and the decreasing field is here. And the resistivity is going down by increasing magnetic field. The number of soliton is change the resistance. Then if we look closer at this part, the final part of this one, we can measure the number of soliton. This one is 1 soliton, 2 soliton, 3 soliton, 4 soliton, 5 soliton, and 7 soliton. We can count the soliton by resistance, magnet resistance. We have the big hysteresis, then we can use multi-step memory on this sample. And this one is direct observation by the Lorentz stem and counting the number of soliton. It's same with the resistance, magnet resistance. And this sample is very special. We roughly gross the crystal. Then this one is left-handed side, and this part is right-handed side, and here is left-handed side. Then this is sandwich, left-handed helix and right-handed helix. The number of helix is 20, just 20 for right-handed. Then if we are increasing the field, the soliton is decreasing, number of soliton will decrease 1 by 1, like this. At the same time, we can measure the magnet resistance at the same. But anyway, we can count the number of soliton by resistivity. Of course, we can measure by the magnetization also. This is field dependence of magnetization, but magnetization. If we measure the very detailed magnetic measurement, we can find the step. This is correspond to the 1 soliton step. But anyway, the chirality is how work on this sample. We can conclude this is coherent spin phase order by coming from the chirality. As you know, the laser is coherent phase photon order, and the normal light is incoherent. But if we consider the charge order state is correspond to superconductivity. And the normal metallic or semiconductor is incoherent charge order. But chirality can make a spin coherent phase order by chirality. But these are the gauge particle, and this one is paired, Cooper paired particle. This is going to the Bose-Einstein condensation can arrive this superconductivity. But spin is impossible if we may consider this Bose-Einstein condensation, but the chirality can generate the spin phase order, macroscopic order. This. Then we can consider not only the one-dimensional case, two-dimensional or three-dimensional. These are I explained today, the one-dimensional soliton case. But if we cut the two-dimensional case, it is possible to generate a skyrmion. It is the same. These are all phase-ordered spin defect. This is two-dimensional. This is soliton is one-dimensional. Then go further. For 1D object with 2D structure is so-called, it's a soliton. It corresponds to this blue plate is soliton. But if go to two-dimensional object with this one-dimensional structure, this is so-called skyrmion. And if go further, three-dimensional object, we can make a hopfion. This is all same topologically protected phase order defect. But this is almost going to finishing. Then the chair is never coming. But here is something interesting. A letter wrote by Albert Einstein to Schrödinger. In his letter, if everything were linear, nothing would influence nothing. What mean? The linear combination is nothing, you know. Harmonic structure carries nothing. But if we make the topological phase defect, it is correspond to tsunami. This is possible to carry something. Then the chirality is very important to generate the phase ordered state for soliton, skyrmion, hopfion. But these carrier can carry something. For instance, information was possible to send by the soliton or skyrmion or hopfion. This is not the linear. Non-linear is a key word. But anyway, this is I want to say today, the crystal chirality and the spin chirality are strongly coupled by Dziaroshinsky-Moriya interaction. And the stabilization of coherent phase order is possible to realize by the putting chirality on the material. This is, I said, magnetic phase order, but electronic also possible, dipole or quadrupole possible. Already we find the quadrupole magnetic phase order in our system very recently. And the generation of topological phase defect is also realized by putting chirality, soliton, skyrmion, hopfion. And the emergence of nonlinear properties is possible to add by the chirality. Nonlinear magnetic susceptibility, electronic susceptibility, and maybe everything possible. I'm going to finish without chair, but anyway, the next Monday, I'll give the talk of the research overview at the 3 p.m. I will talk in this Monday, recent research of chiral magnet and how to expand this chirality to the other field. For instance, QCD problem, we just last year, we published one paper in the quantum chromodynamics using our Hamiltonian to them. And biology also, we are start to collaboration with how aging going. We are doing the age-related disease, for instance, Alzheimer's disease or cataract or our skin itself. How to get the aging by loss of chirality of protein. I'll tell in the Monday. Anyway, just, it is good. Only 20 minutes I need. 50 pages I passed. Then thank you very much.